Yeah, that's pretty much petri dishes.
There we go. And we're the only ones. Nobody's zoomed in. Okay. Solutions. At this point, we're getting to the place where we're actually getting some practical knowledge, stuff that you can actually use. Because everything, there he is. Yeah, we got a copy last week. Oh, yeah, sure. So, solutions. We can identify solutions. Actually, anything can be a solution. Any combination of two or more materials can make a solution, but we're going to focus on aqueous solutions. So most everything that is of interest and useful to the average person is an aqueous solution. So remember what a solution is. It's a homogeneous mixture. Now, as it turns out, we're saying that a homogeneous mixture is synonymous with a solution, and that's true up to a point. Since we didn't discuss the topic of colloids, then it's okay to say that solutions are homogeneous mixtures. Colloid's not a solution, but it is a homogeneous mixture. And you're probably wondering what a colloid is. A good example is Jell-O. It's not, how do you tell a solution from a colloid? You get a clear beaker with your material in it, or a glass, and you shine a light through the side. If you can see the light beam, it's not a solution. If the light beam goes all the way through and you can only see it when it comes out the other side, you got a solution. Okay. It's called the Tyndall effect. Okay, terminology. When we define a solution, we've got a solid, which is most of the time the substance that's present in the largest amount. Okay, you always have just one solvent. You can have one or more solutes. That is, the substance that's the minor component is dissolved in the solvent. Now, you can have more than one solute. We could have, you could make a sugar and salt solution, for instance. You put table salt in there and then you put sugar in it, you've got a solution. But you still only got one solid, that's water. And of course, we define aqueous solutions where the solvent is water. And remember, when we write a chemical equation, if it's in aqueous solution, we always follow the compound or element with AQ for aqueous. So when you have, even if you, even if you make a solution with a solvent that's a major component, and you start off with a minor component. Perfect example is table sugar, sucrose, in water. You start off with a large amount of water and you add some sucrose to it, and you just keep adding it. It goes into solution. Keep adding, keep adding, keep adding. You reach a point where the sugar is the major component because sugar is so soluble. But we still, even at that point and beyond, we still refer to the solvent as water. Because that's what you started with. Okay. Okay, these are types of solutions, just for information purposes. Well, and you probably want to know them. Anytime you have a mixture of gases, you always get a solution, every time. Right? Because there's so much space between the molecules. there's room for everybody. So there's no problem with making that homogeneous mixture. If you have a liquid and a liquid together, like booze or antifreeze in your radiator, those are liquid-liquid solutions. You can even have solids. Two solids make a solution. Brass, alloys, any type of metallic alloy is a solution. Now you can't make the solution with the solids, but you have to melt them, get them mixed together and homogeneous. Then when they cool to room temperature, you have a solid solution. Gases and liquids, right? Soda pop, that's a carbon dioxide dissolved in water with a bunch of other things, actually. And you get a gas in a liquid. That's a solution. And then what we normally think of as a solution is a solid dissolved in a liquid, like salt water. So what happens to ionic substances if they indeed go into solution? They usually break apart. Right? So in that case, we would have sodium chloride going into solution, and it produces ions. The fact that it produces ions is one of the main reasons that it makes a solution, because water is a polar solid. That is, it has slightly positive one side and slightly negative the other side, and it associates well with ions. So the positive side of water will associate with that. What am I thinking of? The negative side associates with that positive. And then these positives will associate with other water molecules or with a chloride ion. And so it's purely electrostatic attraction. It's important to know how your substance breaks up. If you have an ionic substance compound that goes into solution, then it's important to know how it breaks up. Right? So sodium chloride, if we make a 1 molar solution of sodium chloride, we talked about molarity yet? We haven't talked about it. Okay, we will. Then the concentration of the ions, once they break up, is actually twice that. It's twice the concentration. I better move on and get my definitions down first before I start using them. So the solubility of a substance in water is based largely on whether or not it's ionic or it is polar. Polar substances or ionic substances tend to go into solution, whereas nonpolars do not. Just try to mix oil and vinegar to make salad dressing. You can shake it up really hard and get little small beads of oil suspended in your vinegar, but they don't stay there very long. They coalesce and separate. So this is what it looks like when water attacks a sodium chloride crystal. You can see where the orientation of the negative and the positive here, and all it has to do is start. You wonder how does it tug on that ion in the crystal? Well, it's associated here with the crystal, but all around here are more water molecules pulling on it too. Right? So, and as it loosens it there, other water molecules come in. They call that process called hydration. And eventually you get the ion completely surrounded with water molecules. Keeps it in solution. Now, for substances that are not ionic, you look for polar bonds. How do we know they're polar? Well, for this one, we've got ethanol. Okay, so there's your drinking alcohol molecule. And we look for the difference in what we call electronegativity. That is, how strongly does each of these elements pull or attract electrons? If its electronegativity is high, it has a strong attraction. If it's low, it has a weak attraction. And then we look for what are they bound to, right? If one is bound to the same element, then the electrons are evenly distributed between them.
I wonder if there's another H on the other side of that second carbon.
Oh, 1, 2, 3, 4. Yeah, I missed one. Thank you.
Okay. I was really confused. I was like, isn't there supposed to be another one?
Yeah, it was hiding behind this one. That's right. For all organic compounds, carbon needs 4 bonds. Right? You have 4 here and you have 4 there, so we're good. So you look for polarity, that is an uneven distribution of electrons. As far as the periodic table goes, the low electronegative elements, that is, they have a weak attraction for electrons, are down here. And the attraction gets greater as you go up. And it also gets greater as you move to the right. So if you combine those two directions, the very highest electronegative element is right there. Right? And then when you look for polarity of a bond, you want to see what's the difference between the two. So like I said before, if they're the same element, that's a non-polar bond. There's even distribution of electrons between the two. But if you look at oxygen and hydrogen, so oxygen's over here, hydrogen's over there, and in fact they do have a significant difference in electronegativity. You get, well, similar to the water molecule. You get a slight positive, and that little delta means slight, but not complete. If you just put the plus sign, that's an ion. But if you put the little delta, that means it's just a slight distribution difference. And then you have slightly negative here, slightly positive there, because this one has a stronger attraction. And we use a symbol like that, which means that's a symbol for the dipole. So once you have this difference, that's a perfect place for water to attack. Carbon and hydrogen don't have significantly different electronegativity. So these bonds they might be a slight redistribution, but not enough to make it a polar bond. This is the only polar bond in that molecule, and that's the one that water attacks. It forms a weak attraction. It's not like a covalent or an ionic bond. In fact, it's a dipole. It's a dipole in this case. Right, you have slight negative there, slight positive there. So you have 2 dipoles that are attracting one another. And it's weaker than a covalent bond, and it's weaker than an ionic bond. But you get a lot of them surrounding there, and they tend to add up. So that's why ethanol goes into solution pretty well, reasonably well. Now that dipole-dipole bond has a special name. Whenever you have oxygen and some other elements, but for argument's sake, we'll just say oxygen and hydrogen are the primary. They're the majority of these types of dipoles. When they form that bond, it's called a hydrogen bond. And as far as the dipole-dipole interactions go, the hydrogen bond is among the strongest of those bonds. Okay, so whenever you have a polar molecule like this, where it has that polar bond, it will go into solution in a polar solvent like water relatively easily. But if we have oil, which is a type of fat, right? Anatomy and physiology, you guys got that? Okay, we talk about true fats. They're triglycerides. That is, you have, I don't know if you've seen this before. And then you form, oh, excuse me. Then you form long chain there, long chain there, long chain there. And that forms a nonpolar molecule, right? It's a fat or an oil. And that's why it doesn't go into solution, right? Because this long hydrocarbon chain has no polar bonds in it. Right? So the whole thing is nonpolar. And then the fact that you have this one bound to that one isolates this one. So it's not available for forming bonds, hydrogen bonds, okay, in water. Now this is a model of sucrose. You don't have to know how to draw that. The point we're making is, look at all these OH bonds here. There, all over the place. That's why sucrose goes into solution so well. And you can put a lot of it in solution because it has all those potential hydrogen bond sites all over it. This is glucose, and that's fructose. So that's why they say sucrose is a disaccharide. It has two sugars. That sugar and that sugar bound together. Okay. Monosaccharides are just single sugars, like this one, separate glucose, which is the energy transport in our tissues. Glucose goes into the cell, gets metabolized, and we spit out CO2 and water, and get some energy. But it goes into solution because of all these OH bonds. Very polar. So this just illustrates why oil and water don't mix. Okay. Oil's nonpolar, water's polar. So that's why the rule of thumb, like dissolves like. So a polar solvent will dissolve polar solute. A nonpolar solvent will dissolve a nonpolar solute. So you can dissolve oil in a polar solvent, like carbon tetrachloride, good solvent, or benzene. Of course, they're restricted now because they're both really dangerous chemicals. We don't dry clean our clothes with carbon tetrachloride anymore because the workers were getting sick. And we don't use benzene in the lab, except in special cases, because it's also hazardous. But you can still get toluene, right, in your hardware store. Toluene is a derivative of benzene. It just has a methyl group on the top. That makes it a little less toxic, but still a nonpolar solvent. So it's very good at dissolving things like oils. You can thin your paint with it. Oil-based paint. I don't think we use, most of the time we don't use oil-based paints indoors anymore. Because they produce some VOCs, they call them, EPA calls them, volatile organic compounds. We use water-based paints indoors. But oil-based paints are very good for producing a barrier against moisture. So we still use them outside lots of times. Maybe furniture, special applications. And lots of times they'll have linseed oil in them. The advantage of linseed oil is that as it dries, the linseed oil forms covalent bonds between the oil molecules, forms a network that is impervious. You can't break the bonds. So once it gets dried, it takes it a while, but once it's dried, that linseed oil just, it's like an iron barrier against everything. Anyway, so unlike things don't dissolve well in each other. So what's the process of solution? When something goes into solution, it's the conventional wisdom now, chemists believe that three things have to happen. All right, number one, the solute breaks apart. Right? If you have your solute like ethanol, the molecules are going to be interacting with one another. And that's why that they don't evaporate at room temperature quickly, because there's some intermolecular attraction among the ethanol molecules. So before you can put them in solution, you got to break them apart. You got to break those bonds. So you have to add energy. Right? So for that step, you have to add energy. For the second step, simultaneously, the solvent makes holes. To accommodate the solute. So you got to break the bonds that are holding the solvent together, like the water molecules attract one another. So you add energy, so you can bring them apart and make room for the solvent to get the solute to get in there. Okay, that's step one and step two. Step three is where the solute and solvent bond. So you get the whatever attractive forces you're going to have develop between the solute and the solvent, and then that establishes your solution. It's a three-step process. Now, these two, you have to add energy. Right? This one, I'm trying to think of the right word. You don't subtract energy. You get your energy back. You get some energy back. Okay? Now, if you have to put a lot of energy in there to break those bonds, and a lot of energy in to break those bonds, but you don't get all that energy back, you only get some of it back, then you're going to have an endothermic process. What I mean by that is you put energy in, but you didn't get it all back. So some went in, and it's lost to you. Now, in a practical sense, what does that mean? It means it feels cold. Because, say, if you were holding the bag when you mix these together, like in a hospital setting, where you have cold pack bags, where you break that thing inside, you mix them together, and it gets cold. Okay, you're holding onto that thing. Where does it get its heat? Well, from its environment. It's sucking heat out of your hand to do this step and that step, but it's not giving you enough back to make up the difference. Right? So you don't get all of it back. That means it still drew some heat, net energy from your hand. The other possibility is you put energy in, and you get more back than you put in. Then it's exothermic. And that's your hot pack. You break the thing, mix it up, and it takes a little bit of energy to do these, but it gives you a whole lot back and your hand gets hot or warm. Okay? So these are known as heats of solution. Okay, let's see if we can, which one of these will not dissolve in water? Well, these three are in water, and this is in methane. Okay, that's carbon tetrachloride, and it's a nonpolar molecule. So what I'm trying to show there is this is going back into the board, and it forms a triangular base with triangular sides, and they're all regular. That's a tetrahedron. Okay? So that means even though these bonds are polar, right, chlorine is a very strong attractor for electrons versus carbon. But the molecule is symmetric, and all of those dipoles cancel one another out. So that makes carbon tetrachloride nonpolar overall. Okay? So you can think of it as, well, if this one is drawing electrons here and here and here, they're not really isolated. They form kind of a cloud. So it just looks like it's all the same all over, which means nonpolar. Now, if we put something else up here, like a hydrogen, right, then you would get some polarity in that molecule. Okay, so what do we got here? Will this one dissolve in water? No, it's nonpolar. Water's polar. How about ammonia mixed with water? Well, you have to know something about the ammonia molecule. Like that. Plus, it's got two lone pairs of electrons up there. So that definitely means it's polar. So it will dissolve in water. This one has the OH bond. That's methanol. That's the one you can't drink. Wood alcohol will make you go blind. It will mix with water readily. And then this one is kind of a trick question. Nitrogen mixed with methane, they're both gases, automatically a solution. It doesn't matter what their polarity is. Okay, so we talked about what makes a solution and the terminology. But we also have to recognize that there are limits. Right? When you break your solute apart, you make holes in your solvent, there are limits to how many holes you can make. Right? So once you reach that limit, you have saturated your solution. You can't put any more in it. It's got all that it can hold. So as a practical matter, that will be written as something like so many grams of your solute per 100 milliliters of solvent. If you look it up in a reference manual, it's usually given that way. So many grams of your solute in 100 mils of your solvent, or maybe 100 grams of your solvent. And it doesn't have to be water. And then they'll give a temperature, because the solubility is the term we use for it. The solubility is dependent upon temperature. Usually, especially if it's solid dissolving in a liquid, the solubility will increase with temperature. If it's not, if you haven't reached that point, we say it's unsaturated. So those are qualitative expressions with a quantitative limit. So we say it's saturated if it's got all it can hold, unsaturated if it's anywhere below that. It's possible to go past that saturation point. It doesn't happen with every solution, but some solutions you can, if you're careful, because these are very, very unstable. So if you can heat your solvent up and put more, say you want to have 25 degrees, you want it to be super saturated, right? So you heat your solution up to 100 degrees, and you put more of the solute in here, then it will hold at 25 degrees. So you heat it up, get it in solution, and then you set it over on the bench to cool very slowly without disturbance. Because once you, if you pick your amount correctly, because supersaturation has its limits too. You pick your amount correctly, then when it cools down, it may stay in solution. But all it takes is just a little disturbance, like bump the table or tap the beaker, or organic chemists like to reach in there with their spatula and just scratch the inside of the container, and it produces little nucleation sites for the stuff to come out of solution. It just goes bam like that, just drops out. So the lesson here is supersaturated solutions are possible, but they're very unstable. Okay. Okay. We're just hammering this point. Solutions are mixtures, and the amount of a substance that can be dissolved in your solvent varies. It depends on your solvent, and if we stick with water, then we only have to focus on the solute. So if we stick to water, then we only have to say, all right, how much of our substance will dissolve in the solution, and then we need to quantify it. Well, one way I've already shown you, grams per 100 mils of solvent, and that has its uses. Oh, we're going to get some more qualitative. Okay. We're going to get to quantitative expressions of solution concentration in just a second. First, we're going to say if there is a large amount of solute relative to its maximum amount, then you say it's concentrated. If there's a very, very small amount of solute relative to its maximum amount, then you say it's dilute. Okay, now for quantitative expressions. Mass percent is a way that's commonly used by chemists, particularly if they're given a sample and the request is how much of each component is there. They might give it in mass percent. So much mass of a solute per mass of solution. So what that means is let's say grams of solute per gram of solution. So this solution is also a combination of grams of solute plus grams of solvent. Okay, that includes both. And if you're given a problem to calculate the mass percent, and it says you've got so many grams of solute, so many grams of solvent in that solution, don't forget to add the solute in with the solvent for your denominator, because it's grams of solution times 100. Okay? Okay, for instance, 5.5 grams of glucose and 78.2 grams of water means you have to add 5.5 to 78.2 to get the denominator. like that, that divided by that. 6.6% by mass. That's the problem with percent. Percent is a dimensionless number. It just says parts per 100. Right? So what parts are you talking about? Are you talking about parts by mass? Are you talking about parts by volume? So you could potentially have mass, which is the one we just talked about. So that'd be grams per 100 grams. Or you could have mass volume. That would be grams per 100 mil. Usually, that's the interpretation, especially if it's an aqueous solution. Or you could have volume, where you have milliliters per 100 milliliters. This is common for alcoholic beverages, ABV. Alcohol by volume would be percent.
But that's like when it says like 6% alcohol, you know, that.
Yes, it's a volume basis. Yeah, beer is like 6.4, I think. Near beer is 3.2. Wines are like between 11.5 and 16 or 17.
I don't like to see something about for West Virginia brewed alcohol, they raised the minimum up. Or I just read something about it. I was like, what's the point of that? People already make it probably higher than it's supposed to be anyways.
Oh, is that for sales purposes?
I think so, I'm not sure. I glanced at it and I read like 2 sentences of it. I was like, this doesn't affect me. Why am I reading this?
Right. And lots of times they tax it based on the alcohol content.
Oh, okay.
Yeah. So hard liquors are going to have a higher tax associated with them. Okay. Now here's one that in the health care industry you're probably more familiar with, is molarity. And it's just a big M. It means molar. And molarity is a very specific definition. It has number of moles, and the abbreviation for that is little n. Okay. Remember, if we put a 0 up here, that's neutrons. But without the 0, it means moles. So moles per unit volume, and the volume has to be in liters. So you have moles per liter is molarity. It's a very, very, very useful expression of concentration. Because if you want to know how many moles do I have in my hand, if I'm holding, say, 10 milliliters, all you need to know is the concentration, and you can calculate the number of moles you got right there. So 3 molar hydrochloric acid would be 6 moles of hydrochloric acid in 2 liters of solution. Or it could be 3 moles in 1 liter. Right? Or it could be 1.5 moles in 1/2 liter. You know, it's the ratio. This is an intensity factor. It doesn't matter how much you have, the concentration is still the same. Now, relative to that, what concentrated dilute, that's a fairly concentrated solution. The most concentrated solution that I've gotten, you can get more, but that I used in the lab was 37%. That's mass volume. And you take the cap off, and it starts fuming. Because
Did you blow anything up yet recently?
Have I blown anything up?
Yeah. Because I know you had the bottle.
Yeah, no, that was the last incident.
You haven't had any more since?
No, I fixed that problem.
You terrified Miss Joyce.
Yeah.
Someone was dead.
That I was concerned because one of my students was holding it when it went off. He recovered quickly.
That's good.
No, so now what I do is I've got a stash of 2-liter bottles from drinking a lot of pop. And when a group in my lab gets through doing this experiment, that bottle goes in the trash. And I just bring a new one in.
Like, we had just finished talking about, because she always tells us, like, there's a sugar or something, like, she's like, run, and she's like, zigzag. And we were just talking about something like that, and then that went off, and she, like, jumped, and her eyes got real big.
Sounded like a gun.
Yeah. Which we were right there with you, like, on the other side of the lab. So
Oh, yeah, it must have been loud.
Mm-hmm.
Yeah. And my ears were ringing, because I wasn't that far away from it
You were
either.
close to it.
Yeah. Yeah, that bottle, I mean, it tore apart in several places. Okay. So, if you have 1 mole of sugar and 125 milliliters of solution, how do you calculate that? Always go back to this formula. So we have 1 mole. So how many liters is 125 milliliters? Move the decimal place to the right, 3 places. Right? Tens, hundreds, thousands. Okay? And just divide that out, and you get 8 molar. So that's fairly concentrated sugar. Now, while we're doing this, it's important to recognize that this is great because it tells you how many moles and how many molecules you have or how many atoms you have. Doesn't matter how much they weigh. But if you're going to make up a solution, we don't have a balance that measures in moles. It's always in mass. So you've got to have a conversion in there. If you're going to make up a solution with so many moles of sugar, you've got to convert that to mass so that you can measure it on your balance. Here's a perfect example. What's the concentration of solution we have? We have 500 grams of potassium phosphate. Now this brings up the topic of actually why I hammered so hard on formulas. You've got to be able to write the formulas, but you'll never know how to convert that to moles. So potassium phosphate, we know it's got potassium. Phosphate is a polyatomic ion, which is PO4. Potassium is from the first group, which means it's a +1 charge. Phosphate is polyatomic with 3 minus. So +1, 3 minus, that means we need 3 of these, and that's your formula. Then to convert 500 grams, you need a conversion factor. Moles and grams in this relationship means molar mass. So you take 3 times potassium, like 39, 10, 1 phosphorus and 4 oxygens, and you get a value there. Okay. 212.27 grams per mole. So then you divide this into that, and it's a little less than 2. Wait a minute. Or is it 2? 212? Oh, it's greater than 2. Right. If this were 250, it'd be 2, so that would be greater than 2. Oh, there it is. So you've got that many moles in this many liters. Okay.
Please excuse my dear Aunt Sally.
Yeah.
That's probably one of the things I do remember, like, from high school.
So if you don't have parentheses in the right place, you gotta revert to PEMDAS.
There's a lot of people who still don't like know that and remember that.
Oh.
Yeah, I know a lot of people that it's like on Facebook, they'll post like problems that have parentheses, exponents, multiplication, division. It's like a big long equation.
Mm-hmm.
And most people get it wrong. Even people I went to school with that I was in math class with, they get it wrong because they don't know how to follow it.
Yeah. Okay. So, and you can work your way back. I mean, it's like any formula, right? If you know two of these, you can find the third one. Right? So maybe you know this one already. And you know, I need so many moles here. So you solve for V. Right? Is that right? So, what volume gives you that many moles at this concentration? What if you know the molarity and you know the volume that you possess? You want to know how many moles there are. Like that. Can you see most of the board from where you're sitting? Okay. So, and most glassware is not calibrated in liters, like tenths of a liter. It's usually in milliliters. So that would be 200 mLs.
It used to be in CC, but now it's mLs. A lot of our syringes, they still say CC, they also say mL. They
Right.
give it, there's a 3 cc syringe, and then
10.
Yeah, there's a 10. I was like, I think there's a 10 as well that we have.
Might even have 20 or 50.
I think we do have a couple. We only use them a couple times, but I
Just
think
the
we
big guys.
do have one. It's just.
If you're going to irrigate a lot, you probably use a big one. Yeah, and of course, mLs and cc's, same size.
When I first got when I first was like a medical assistant, we was learning that in high school. I was so confused. I was like, which one do they prefer me to use? But then I realized it's all the same. It doesn't matter.
And then the world was bright again.
Oh yeah. I stressed about that for a good week.
Okay, so this slide just makes the point that if we make two solutions, one with sodium hydroxide and one with potassium chloride, those are our two separate solutes that we're going to put in solution, and we have equal mass of each one, what's your intuition on the concentration if they go in the same volume? They're going to be different concentrations than molarity, aren't they? Because sodium hydroxide is 1 molar mass, potassium chloride is a different molar mass. So there's your sodium hydroxide. This means moles, and this means liters. So that gives you 10 molar sodium hydroxide. That's very concentrated. And if we do the same thing with potassium chloride, see the molar mass is higher, right? So we're going to have lower molarity because we have fewer moles, right? Almost half. Okay. Now let's get this one. Here. Now we go back to my second or third slide where I was talking about when your ionic compound goes into solution, what does it become in solution? Right? Sodium chloride becomes 2 ions, so you double the concentration. Calcium chloride becomes 3 ions, calcium and 2 chlorines. Right? So if it's 0.25 molar, that compound, total ions will be 0.75 molar, 3 times that value. Each one, let's see. Right. The calcium will still be the same, right, because it's a 1-to-1. But the chloride will be twice that, 0.5. Now, why is that important? Well, from a physiological standpoint, if you want an isotonic solution for your patient, and you make it up, say you're going to make it up with, and you know that 0.9% sodium chloride is isotonic. Well, if you say, oh, I don't have sodium chloride, I'm going to use calcium chloride. So let's make up 0.9% calcium chloride. Well, you're going to end up with 50% more ions in that solution than need, and your patient could be in trouble because that's a hypertonic solution. It'll draw water out of their cells.
I learned about that in anatomy and physiology. I find something like that.
Yeah. Yeah, you want an isotonic solution. Now, of course, you would only use that 0.9% sodium chloride in emergencies because there are other effects, right? It's not just isotonic. How much sodium and how much chloride can your kidney stand, right? So when you give somebody a sodium chloride, if you give them a sodium chloride isotonic solution, you're giving them about 10% more sodium than they need, which is doable by the kidneys. But you're giving them 50% more chloride than they need, which is difficult at best for the kidneys. So that's why isotonic solutions are usually made up with non-ionizing materials. Like, for instance, lactated Gringer solution. They use lactose instead of the salts. And then you don't have that problem because your body can metabolize lactose. Most people. Except for the lactose intolerant.
I know a couple people like that.
Anybody else need a break?
Yeah.
Yeah, go ahead and take a break. I'll pause the video. Just okay. So, I should have turned that light off. Wouldn't get so much glare on the screen. That is better. All right. So which of the following has the greatest number of ions? Well, in order to do something like this, I invoke Henry Ford. I set up an assembly line. So you have 400 mils of 0.1 molar sodium chloride. 400 mils of 0.1 molar sodium chloride. You have 300 mils of 0.1 calcium chloride. Oh, wait a minute. Those are the same concentration. Well, that's all right. I'll just go ahead and put them up here anyway. And then 200 mils of 0.1 molar ferric chloride, iron 3 chloride, and then 800 mils of 0.1 molar sucrose. Okay. Question is, which has the greatest number of ions? Well, easy. That makes no ions. Sucrose does not dissociate. Okay, so we can focus on the top three. So, since they're all the same concentration, you need to know two things. How much do you have here, and how many ions do you produce there? So, 0.4, remember, molarity equals this, that, that. So the number of moles of ions would be this times that. So if we, molarity times volume, 0.1 times 0.4 is 0.04, right? And this is 0.03, and this is 0.02. That's molar compound, right? But this one makes 2 ions for each. This one makes 3 ions, and this one makes 4 ions. So this one would be 0.08 molar ions. This one would be 0.09, and this one would be 0.08. So that one has the most moles of ions, greatest number of ions. Okay? And you wouldn't know that if you didn't actually just work out the problem. And when I say Henry Ford, I say, this calculation is done exactly the same as this one and exactly the same as that one. You just change the numbers based on the data you have. Okay. Oh, so probably going to tell us that. Yeah, there it is. So there's your winner. Okay, that's the author's idea of how to solve the problem. So what's a standard solution? Anytime you see this word, it means that you can compare other things to this one because you can rely on its, in this case, concentration. That's the standard, and we measure everything else against that. We know, in this case, we know its concentration very accurately. When we do titrate acids against bases in other classes, I have a standard solution of acetic acid, 0.873 mole. It's very stable over long time periods, so I use that as the standard. The base, sodium hydroxide, is not stable. Exposure to air converts it to sodium carbonate. It precipitates out, and the concentration of sodium hydroxide then decreases as that happens. So every year we have to re-standardize it against that same acetic acid. There are other ways to standardize, but that's simpler for a student lab. In many cases, you can prepare a standard solution. Right? So what we have here is a volumetric flask, right? And they always have this big bulb at the bottom and a narrow neck at the top. The narrow neck is so that you can see a change in volume very easily. And there's a mark on it, right, on the neck that tells you when you have the rated amount of volume that flask will hold. Say if it's a 1 liter flask, when it reaches that mark, you have 1 liter in that flask. And of course, and these flasks are calibrated. They're calibrated so that when the solution reaches that mark, aqueous solutions in glassware form a meniscus, right, like that. And they're calibrated to read at the bottom of the meniscus. Right? So once you get this filled up here, it's going to give you a meniscus like that when you have the right. You don't read at the top or on the edges, you read at the bottom of the meniscus. So you measure out a known volume, a known mass, in this case, of your solute. And of course, your solute, you need to guarantee that it's dry. Right? You don't want to weigh the water too, you just want to weigh that solute. So you heat it, say 105 degrees centigrade, just above boiling, for several hours in the oven, and then you let it cool down inside a desiccator, which is a glass or a plastic jar with some stuff in the bottom of it that absorbs moisture. Right? Calcium sulfate is a good choice. And it'll suck the moisture out of the air, so as it cools, it doesn't pick up moisture from the air. Right? Then you can pull it out, weigh it, put it in your flask, and you know you have exactly that weight. And of course, you can convert that to moles because you know what the compound is. So then you dissolve it right? You add enough water to solubilize it, and then you wait. Most solutions are either exothermic or endothermic. So when you change the temperature of your solution, you change its volume, right? And you don't want it to be hot or cold when you go up to this mark, because once it cools down, it won't be on that mark anymore. That's the problem with molarity. It's dependent upon volume, which is dependent upon temperature. But once it's come to room temperature, then you can finish diluting it to its mark. And then you cap it and mix it. Then you have your solution of a standard concentration. So these are the things that could go wrong. You could weigh it wrong, or you could transfer the solid and lose some in the process. Right? That's very common. You could put more in your solution than it will hold, right? You want to make a 5 molar solution of something, but it becomes saturated at 4 molar. Then you're not going to have a 5 molar solution. So you have to be careful with that. That's why the tables in these reference manuals, you look up and be sure that you're below your saturation point when you're mixing up your solution. You could misread the volume mark. What if you're looking up here like this, or like this at an angle? You're gonna misread the position of that meniscus, right? You gotta have eye level. Right? So you either sit it on the bench and adjust your eye up and down so that you can see level across, or like I do, which is not necessarily the best way. I grab the thing, hold it up in my eye, and use my squirt pump to finish it off. If you have to do 100 of these a day, then you just do it. So if you generate a lot of heat, or you suck up a lot of heat in the process, and you don't let it come to room temperature, that would be a source of error also. Now, if it's endothermic and it gets cold, that means the volume is going to shrink. So it would be okay to bring it to the mark, because when it heats up, wait a minute, no, if it's, hold on, if it's exothermic, excuse me, if it gets hot, it's going to be more volume than you expect at that temperature. So you bring it up to the mark, and as it cools down, it shrinks. That's safe. If it's the other way around, endothermic, bring it to the mark, and then as it heats up, it goes like that, and you're screwed. So, one of the other things that we used to do in the lab, because we used a lot of solution, primarily in soil extractions, we needed a definite concentration, but we didn't want to have to make up that dilute solution every time, weigh out the stuff. So we make up a concentrated solution. And then whenever we needed replenishing our working solution, we just dilute it. Right? So you need to know how to dilute it so you get the right concentration. Well, if you have a concentrated solution over here, and you want your diluted solution over here, right? And you know what your volume is over here. So if you take out a certain amount of that concentrated, and then you put it in here, and you increase the volume of solvent, which means the amount of moles that you put in here is distributed over a larger amount that dilutes it. Right? So how do we tell how many moles are in here, in that sample? Well, we know the molarity here of the concentrated, and if you know the volume of the concentrated, that gives you the number of moles. Right? Okay, so you know how many moles you got here. You're going to put that number of moles over here. Now, when we dilute that number of moles, did we change the number of moles? as long as we didn't spill any, we got the same number of moles over here in the diluted side. So the diluted side then is also equal to molarity times volume, only now we have diluted molarity in this total volume, right? What's that mathematical property? I'm trying to think of the word. If A is equal to B and B is equal to C, then A is equal to C. That's what I'm trying to think of. There's a word for it.
I know what you're talking about.
Anyway, we'll just use it without naming it. So if this one's equal to that one, and that one's equal to that one, and this one's equal to that one, then these two are equal. Right? So we can say that the molarity of the concentrated times the volume that we took out of it is equal to the molarity of the diluted times the volume that it represents. Sometimes I write it this way. M1V1 equals M2V2. When you do it that way, you've got to know which one's concentrated and which one's dilute. But when you use these subscripts, then it's given to you. So that's how we dilute things, that relationship. The other thing that's nice about this relationship is these are ratios, right? You can rearrange this formula to put M over here and V over there. If the V's are on both sides and one is in the numerator and one's in the denominator, what does it matter what their units are? They cancel, right? So when you use this ratio, you can keep milliliters here and milliliters there. You don't have to change it to liters. That saves you a step. If you're using the original formula where molarity equals moles divided by volume, and that's all you're using, you do have to have volume in liters. Right? But when you're using the ratio, you can use milliliters. Okay. So let me see. I want to be sure I get all this covered. A half-molar solution of sodium chloride in an open beaker sits on a lab bench. Oh, which of the following would decrease the concentration of the salt solution? Okay. So the first point here is that sodium chloride is not volatile. Right? If you start with a half-molar solution, you've got so many moles of sodium chloride in that solution, and the only way you can get it out is to dip it out. So how do we decrease the concentration? We work on the solvent. Change the amount of solvent. So if you add water to the solution, you're increasing the solvent and decreasing the concentration. Because of this relationship, if that's constant, then we have to increase this one to decrease that one. To make this one bigger, that whole unit gets smaller. That makes that smaller. So that's how you decrease the concentration, which is what we did with the dilution. So that's a decrease. Pour some of the solution down the sink. That doesn't change the concentration at all. Wait a minute. No, it doesn't change it at all. That's a mistake. Where is it? Here it is. That's no change. No change. Add more sodium chloride. Okay, if we add more solute, we do increase the concentration up to the saturation point. Let the solution sit out on the open bench. Since sodium chloride doesn't evaporate, water does, then you're decreasing the solvent an increase in concentration. So only one of them will actually decrease the concentration, this one. And that one's an error. So let's see. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 8.8 molar? So in this case, it's probably a good idea, so that you use the formula correctly, to say what's concentrated, dilute, and dilute. Before you put them in the formula, identify what your information is. The minimum volume of 2 molar, we're going from 2 molar to 0.8 molar. So 2 molar is concentrated to 0.8. Okay, so we got that in the right order, dilute, concentrated. And we want to make 150 milliliters of final solution. So this is the unknown, right? So you just set up your relationship, concentrated, dilute, dilute. Plug your numbers in, solve for your unknown. Okay? Well, this slide I use in view. You have to go? Oh, to class. Oh, yeah, sure.
Is this recording?
Oh, yeah. I hope. Yes, it is recording.
Okay. I'll catch the rest of this on the.
Okay. We'll do a review next week.
Okay. Thank you.
Okay, so it turns out, and we didn't have to change, we just used milliliters, and our answer comes out in milliliters. Okay, so the next thing you would want to do is use, go back to stoichiometry, balanced equations. You know what you start with, and maybe you want to know what you finish with, or you know what you finish with, and you want to know what you can start with to get there. In order to use concentration values in a stoichiometric equation, we would have, say, let's see, example. Let's say we have silver nitrate in solution, and we have sodium chloride in solution, and we put these two solutions together. The silver is going to combine with the chlorine and make a solid. It's going to precipitate. And then the sodium is going to combine with the nitrate and it's still in solution. So it really doesn't combine. And that's balanced, just like it is. So since these are in solution, our stoichiometry is not like previous equations where we had mass and we had to convert it to moles to get to one side or the other. In this one, we would have a concentration in so many milliliters, and concentration in so many milliliters, and that would tell us how many moles of each one, because we use molarity times volume, would give us the number of moles. Right? Then we can say which one is limiting. Right? So it's the same procedure. Once you've got moles, then it doesn't matter where they came from. You can convert, find out how much silver chloride you could produce as a solid. The word is precipitate. These are solutions. Silver chloride is not soluble to any great extent. Drops out of solution, and we can tell, all right, how much did we make? That's in stoichiometry. And that's basically what this is saying in green letters. Here's an example. So we've got 10 mils of sodium phosphate. Right? We have to know how to write that. And then we combine it with 20 mils of this concentration of lead 2 nitrate. And then when we, well, the question is what precipitate will form? All right. Well, in that case, you've got to be able to write the compound, sodium phosphate in solution, and then lead 2 nitrate, in solution. And then this is a double replacement reaction. Right? You just swap the cations, like that. So lead and phosphate is one possible product. So lead 2 and phosphate, so it's 3 here, 2 here. And then sodium nitrate, which is soluble. Did we do that yet? Hold on a second. With that, at the one of the last pages, useful information, you got this chart. Yeah, we have done that, right?
Oh, yeah, that's all you do.
So you just look up, after you do this double replacement where you swap the cations, then you say, are these soluble? We know that one's soluble. And then check this one, follow the lead, and then down the phosphate, and you find out it's insoluble. So that forms a precipitate. Oh, okay, so what was the other? I forget what it was asking. Well, then you want to find out which one, how many moles of each you start with. And then you find out which is limiting, and that tells you the maximum amount you can form of your solid. We're running kind of short of time here. Sodium phosphate reactant. Okay, there we go. Lead 2 nitrate. Okay, so now we get 10 mils of this one at 0.3, 20 mils of that one at 0.2. And you find out how many moles of each one. And you don't have to say 10 mils at 0.3 molar and 20 mils at 0.2. 20 mils at 0.2 molar. If you multiply molarity times milliliters, you get a unit called the millimole. Okay. So if we multiply these two together, that would be 3 millimoles. Okay. And this one would be 4 millimoles. Okay. We have to balance the equation though first, right? So we need 3 of these. That gives 6 of those. We need 2 of these. That gives 2 phosphates. 2 phosphates. So we're balanced there. Well, we're probably going to have to go moles anyway, because we're going to have to convert. Well, actually, we don't, because we know moles here. If we have 3 millimoles of these, then 2 of these for every 1 of those. So that means this side would make 1.5 millimoles. Make half as much of that. And this one would make 1/3 of that, so it'd be 4/3, which is what? 1 1/3, 1.3. So this is your limiting one right here. So 1.3 millimoles is all you could make there. Then if you're going to determine mass, you will have to convert to moles. So 1.3 millimoles times 10 to the minus 3 moles. Right, because a milli is minus 3. And then you can convert that to mass. Okay, so there's a balanced equation. Here, there, there. Okay, find the limiting reactant. All right, we went ahead and used moles here. That's okay. So we find out what the limiting reactant is. Oh, we're saying it's lead nitrate. Oh, yeah, that's right. That's right. And then you can convert that to, actually it's 3 through 3, isn't it? And convert that to how many grams of lead phosphate you have. Okay? So what's the concentration of nitrate ions in this situation? Well, nitrate's not consumed in the reaction, it's a spectator. So all you have to do is find out how many moles of nitrate you start with. Right? So it's 2 moles for every 1. So it'd be 2 times this would be 8 millimoles of nitrate. But we're adding a volume from here and a volume from here. So it's this many moles per 30 milliliters. And if you divide millimoles by milliliters, you get molar. So it'd be 30 into 8. And that value should be something, spectator. There it is, 0.27. Is that right? Yeah, 0.27 molar. The key there is 2 keys. Recognize that it's a spectator, so it's not consumed. Everything you put in is still there as an ion. And then recognize that you are diluting it. Right? You start out with this much volume of it, but you're adding this volume, so that changes, it dilutes it. What's the concentration of phosphate ions? Well, in that case, this is an excess. So what you have to do is say, all right, how many phosphate ions are we using? This many moles of that. And twice that of phosphate ions. And then you come back over here and say, well, if you got that many moles of phosphate ions used, then you subtract the used from what you started with, and that's what you got left over. Okay? So you can go lots of different places with this information, and that's just cannon fodder.
Did you put the Zoominator on the computer?
Yeah. Joyce insisted on a name, so I had to make something up. Okay, let's see. Is there anything else we can talk about here? Oh, you remember net ionic reactions? Remember how to write those? We did that, didn't we? Right. So you just say, this is ions, that's solid, and that's ions. And then you write them all out. And then you cross out the spectators. That's your net ionic. The net ionic is going to be lead, phosphate, yields that compound. Okay. Oh, we got more? I thought I was done. Neutralization reaction. What do we got? 3 minutes? Okay. Acid-base reaction is neutralization. So you have it. To recognize an acid-base under most circumstances, but not all, most circumstances, your acid will be written with a proton, 1 or more protons, and then something else on the other side. So it could be 1, it could be 2, it could be 3. And then your base will have hydroxyls. And the base, the cation and the anion combine, and the H and the OH combine to make water. Okay, so this is your acid, this is your base, this is a salt by chemical definition, and water. So the net ionic equation here, this is usually in solution. It doesn't have to be. But if it's still in solution, then spectator, spectator, spectator's gone. And the net ionic equation for an acid-base reaction is that. Hydrogen ions plus hydroxyls yield water. When you're going to do some stoichiometry, it really just depends on how many of these are in the base and how many of those are in the acid as to what the stoichiometry is. Right. In that case, let's back up. Next one. There. So if we react sulfuric acid with sodium hydroxide, it's got 2 hydrogens, but only 1 hydroxyl. So it's going to take 2 sodium hydroxides to match that two hydrogens here. So if we write the equation, where is it? Better be in there. There we go. So there's your sulfuric acid, and you need 2 sodium hydroxides to get you that. And sodium sulfate is your salt. All right. If you have any problems that use equivalents rather than moles, then we'll talk about them when we look at review problems. Otherwise, the concept of equivalence is useful if you're going to do these things day in and day out. But you can accomplish the same thing with stoichiometry. And the term is normality. So the number of equivalents per liter is normal. So 1 normal hydrochloric acid only has 1 hydrogen, is the same as 0.5 normal, 0.5 molar sulfuric acid, because it has 2 protons. So they're both 1 normal, but sulfuric acid is a half molar. Okay. I think I bored you to death. That's enough for now. And we'll look at this on Thursday, I guess.
Next time.
Next time, yeah. Mark this out. Oh, better stop that thing too. Go ahead.
Thursday is a review.
Yeah, Thursday will be a review.